Okay, so today we're going to study CP and CPK. This is a lot more in depth than you will need on the exam, but if you want to know how to figure CP and CPK, this will work for you. So we're going to start out with a YouTube video here.
Says that it's okay, but
Start at the beginning.
let's consider the purchase of a vehicle. As the customer purchasing a car, you're going to have several requirements. You're going to want the car to perform a certain way. Those characteristics of performance might be something as simple as comfortable seats, perhaps an engine that has certain amount of horsepower, and perhaps an aesthetic body design, the outside appearance of the car. The product performance that you require as a customer is then translated into some kind of specifications. The customer specifications are then taken by a design engineer. And for example, let's say one of your characteristics is a comfortable seat. The design engineer will decide what kind of technical specifications will meet your requirement for a comfortable seat. So he'll come up with something like, well, in order to be comfortable, the seat needs to be a certain softness. So I need to make it out of foam. So he'll come up with that specification. It needs to be made out of polyurethane foam. Next, he'll assign some kind of durometer hardness to that foam, maybe a 45 in the Shore durometer hardness scale. Um, Once the design engineer has specified the technical specifications, it's then up to the process or manufacturing engineer to determine what specifications will be used on the production line in order to meet those design specifications. In the case of foam, it might be, well, we're going to use polyurethane foam in a ratio of 1 to 1.6, and we're going to have to meet a density of maybe 400 kilograms per cubic meter for the foam to be this 45 durometer Shore A hardness value. So the manufacturing engineer then translates the design specifications into manufacturing specifications that are used on the production line in order to meet those design specs. We've gone through the product design process, translating customer requirements into design specs, and then from there, we've gone through the design for manufacturing and translated those design specs into our process specifications. Now that our production line is up and running and creating, let's say, our foam seats, a very important question to ask, are those foam seats meeting the specifications of the customer? Are they meeting the design specifications? How do I know if my process is meeting the customer's requirements? Are there certain tests that I can do? Are there certain samples that I can take or measurements that I can take? Companies might have varying answers to that question. In one company, they might say, well, if I don't have any customer complaints on this product, I could assume that the product is meeting the customer's requirements. Another company might say, well, we measure the number of warranty claims. And depending on the number of warranty claims that we get in a year, that tells us how well a product is meeting the customer's needs. Another company might say, well, what we do is we measure the number of rejected parts or returned defective parts from a customer. So if we have over a certain limit of returned products, then we realize that there's something wrong with our production process. Those answers, although common um, and some value in them, are not the best way to know if our process is meeting a customer's requirements. Another option is to think, if I have a control chart, I could look at a control chart and it will tell me something about whether I'm meeting the customer's requirements or not. When I look at a control chart, I see data points of my subgroup averages that tell me the performance of my foam product with respect to the density. I have upper limits and lower limits that tell me where I expect the process to perform. So it's very tempting to say, well, if I look at a control chart, I can tell whether or not my product is meeting the customer's requirements. That is not the case. An upper and lower control limit in a control chart, while they may tell me where I can predict that the process will be, assuming the process is in control, and that's an important and very critical assumption. While they may tell me where I can predict the process will be, they have absolutely no relationship to the customer's specifications or the design specifications. The upper and lower control limits are calculated from a formula that uses subgroup averages from the process. They don't use specifications or tolerances at all in their calculations. It is simply a measurement of the process. So while a control chart does tell me how the process is doing, it doesn't tell me where it needs to be or where it's supposed to be. In fact, I could have a control chart that is in control, as we can see on the screen, like this, random variation, exactly as it should be. So I could have a process that's in control, and it could be completely outside of my specification limits. The control limits do not tell me anything about where it lies in relation to the specification limits, where it lies relative to what the customer actually wants. So back to the question, how do I know if my process is able to meet the specifications the customer requires? What can I do to figure out if this process we have is capable of manufacturing to the specifications that are required? We take the specifications and we divide them by the process width. Our specification width is simply a function of our tolerances. In other words, it's our upper specification limit minus our lower specification limit, and we divide that by our process width. This fraction is known as Cp. We'll start by calculating the numerator, the specification width. In the example of our foam seat, our specification density, we'll say, is 450 kilograms per cubic meter plus or minus 15 kilograms per cubic meter. That's the specification given to us by the design engineers. 15 is the tolerance, so plus or minus 15 from the nominal of 450. Therefore, our upper specification limit is 465 and our lower limit is 435. The specification width is calculated by taking the upper specification limit minus the lower specification limit, or 465 minus 435, which gives us a specification width of 30 kilograms per cubic meter. The next step is to calculate the process width. Let's take a look at a control chart. A control chart tells us information about our process, how it's performing. Recall that the center line of a control chart is the average of all of our subgroup averages. And about that center line, I have plotted this gray line. The data points represent the subgroup averages, or I've taken samples and I've averaged out the values for those samples, and I've grouped them together, generally in groups of 4 or 5 units, and plotted them on this chart. I've also calculated upper and lower control limits. So a control chart is useful because it's telling me what the process is doing. It's the voice of the process. It tells me how it's performing, and when it's in control, it tells me where I should expect future products to fall within. In other words, if my process is in control, I expect that all of the subgroup averages will fall within these upper and lower control limits. There is, however, one interesting thing to consider. These data points are subgroup average values. So I expect my average subgroup values to fall within the upper and lower control limits. Let's ask the question then, what about individual product values? Should I expect individual product values to fall within these control limits as well? So to answer the question, will these individual data points fall within the same control limits of a control chart? What we'll do is we'll look at a number of individual samples. So what we've done is we've gathered about 200, over 200 samples of, say, foam for these foam seats. We've gathered 210 samples of foam, and we've measured each of these values for foam density. And then what we're going to do is we're going to plot them on a histogram. So what I've done here is I've plotted all of the individual data points for these pieces of foam, about 210 of them, and I've plotted them in a histogram to show the dispersion of the individual pieces. So we see that the foam density ranges from about 420 kilograms per cubic meter to about 500. So it's normally distributed and looks fine and looks like a fairly broad range of values. These again are the individual samples, individual pieces of foam that I'm measuring, and there's about 200 of them, 210. To compare the individual data points with average data points, I'm now going to combine samples into subgroups, similar to what I do for control charts. So let's say that I've combined all of these samples into subgroups of about 10 data points each, and so now I have about 21 data points. When I plot the histogram showing the foam density of these subgroup averages, I notice a drastic difference. For one, of course, I do have fewer samples, or fewer data points, because I've only got 21 data points in this histogram. I'm still using all 210 samples, but they're now averaged out into 21 subgroups. So the 21 subgroup averages have a much narrower dispersion than the individual data points. As you can see here, the foam density average ranges from 450 to about 470, whereas the individual data points ranged all the way from 420 up to 500. So to answer the question, is there more variation in individual data points versus average subgroup averages? The answer is yes, of course. So then to answer the previous question that we asked, do we expect individual data points to fall within the control limits of a control chart? The answer is no, we don't expect them to fall within those limits. As shown here, we expect there to be more variation in individual data points. So we would expect some products to fall outside of control limits if they were plotted as individual data points. So then the question is raised, how do I calculate, or what do I use for my process width? If the process width in a control chart is not going to capture all of the individual data points, then what do I use? How do I come up with my process width?
The process width is going to be a function of my standard deviation of my population. So somehow I'm going to use the standard deviation of my population to figure out what my process width is. Let's take a look at the control limit formula. The control limit formula contains a standard deviation of sorts. If we look at it, we see that the upper control limit is x bar bar plus 3 times sigma, and I've added in here sub x. The reason that sub x is there, that subscript, is because it is not the standard deviation of a population. The standard deviation used in the upper control limit formula is actually the standard deviation of the subgroup averages. The specific term that we use to calculate this number is A2 times R bar. A2 times R bar is an estimate of the standard deviation of subgroups. In other words, it's an estimate of the standard deviation of this set of values here, not this set of values. In capability, I'm concerned with standard deviation of the individual values. As we can tell from looking at the histograms, the standard deviation of these subgroup averages is very low compared to the standard deviation of all of the individuals of the population. And just a side note, even this histogram here is a sample of the population. It is not the entire population. So even when calculating the standard deviation of this set of data points here, we still need to come up with an estimate for the population. There is a relationship between the standard deviation of the subgroup averages and the standard deviation of a population. That relationship is found in this formula here. This is the standard error of the mean. You've probably heard of it before in your statistics class. The formula for the standard error of the mean is the standard deviation of the subgroup averages, or sigma sub x, is equal to the standard deviation of the population divided by the subgroup size. This relationship connects the subgroup average standard deviation to the population standard deviation. This formula here is the concept. We will not use this formula to calculate our process width. Walter Shewart came up with an estimate for the process width that we're going to use. This formula, however, is the concept and does show the connection between the population standard deviation and the subgroup average standard deviation. Let's take a look at some data and walk through an example. The data used to calculate capability is going to be organized very similarly to data used in a control chart. And in fact, we're going to start off by creating a control chart from the data. Over on the left-hand side in column A, I have the density of, we'll go back to our foam example from the car seat foam. I've got density listed in column A. For this specific example, I actually have 210 data points. Column B, I've listed those in subgroups. Essentially, it's the location along the production line that the sample was taken, so a fairly logical division of subgroups. And column D, I've calculated the average density for each subgroup, the range of each subgroup, and then finally the standard deviation of each individual subgroup. It's important to note here that the standard deviation of this subgroup is just a simple formula. I've just used Excel's formula for the standard deviation of a sample. So that's stdev.s, not the .p formula. So that's the simple formula that I've used to calculate the standard deviation of each subgroup. So for my control chart, I'm going to start off by calculating the x bar, which is equal to the average of all of the subgroups. So I have 21 different subgroups representing 210 total data points. The average of all of the subgroups is 465. Now I'm going to calculate my range average, or my R bar. And again, I'm doing this in order to calculate and create a control chart. Now my upper control limit and my lower control limit are simply x bar plus R bar times A2, and A2 in this case, I have a sample size of 10. My A2 value from my appendix is 0.308. So my upper control limit is 479, or rounded over to 480. My lower control limit is 465 minus 0.308 times R bar, so 450 is my lower control limit. I'm going to create a table of my X bar values and my upper and lower control limits in order to make it easier for me to create the control chart. So I'm going to list here in column K my X bar values. Because I've merged the cells, it's a little bit difficult to create the control chart in with a simple table. So I'm going to create this new table here. Starting out in D3, my next one is at D13, D23 is the next one. It's a little tedious, but it'll save me some time in the long run. Okay, so I've got my X bar values listed. Next, I want to list my lower control limit and my upper control limit and my X bar values. My lower control limit is equal to 450. And here I'll make sure that I lock the cells so that when I drag these down, that I don't end up changing my value. My upper control limit is 480. And then my X bar value is equal to 465. So now I have all of the data to create a control chart. I'll simply select the data and create a line chart. Okay, so now I've created a control chart. I can see that the data is in control, so I can confidently move ahead and calculate my capability. Now we haven't quite figured out how we're calculating our process width yet. So let's walk through that right now. And of course I should put labels and titles on my graph, but we'll leave that for later. A moment ago, we talked about the relationship between the subgroup standard deviation and the population standard deviation. Sigma sub x being equal to the standard deviation of the population divided by the square root of n. For the purpose of this exercise, let's run through that. We know that we're not going to use this, but we will run through it right now just for the purpose of showing what kind of value it would give us. Recall that sigma x is the standard deviation of the subgroups. In my upper control limit formula, that's represented by A2 times R bar. However, that formula estimates 3 sigma, so A2 times R bar is actually 3 sigma. In order to estimate just sigma x, I'm going to say A2 times R bar divided by 3. The estimate for sigma x is 4.95. To calculate sigma, the standard deviation of the population, I now need to rearrange this formula of the standard error of the mean. Rearranging that, standard deviation of the population now becomes sigma x times the square root of n. N is 10, my subgroup size is 10, so I take the square root of 10, multiply it by sigma x, and the value I have for the standard deviation of the population using the standard error of the mean is 15.6. Rather than using the standard error of the mean to calculate the standard deviation of the population, as we've just done, industry standard is to use a different formula. Studies have shown that an estimate for the standard deviation of the population, or sigma, can be calculated using the following formula. S bar divided by factor C4. In this situation, S bar represents the standard deviation of subgroups, and C4 is a factor from a table in the appendix of your textbook. Studies have shown that this estimate more closely resembles the standard deviation of the population. Another estimate for sigma uses the formula R bar divided by D2. Both of these formulas are acceptable and industry standards when calculating our process width. R bar, of course, is the average range of the subgroups, and D2 is a factor in the appendix of the back of your textbook. Now, C4 and D2 are both dependent upon the subgroup size, and take note that D2 is a lowercase d. In your appendix, there are actually 2 factor D2s, one being a lowercase and one being an uppercase. We've determined how we're going to calculate sigma, or the population standard deviation. Now that we've figured out a formula for the population standard deviation, I can begin to calculate my process width. My process width is going to be plus or minus 3 standard deviations of the population. That's simply by definition, similar to the control chart being plus or minus 3 standard deviations of the subgroups. Process width is also equal to, of course, then 6 total standard deviations. Because I've calculated my standard deviation of the population as being equal to S bar divided by C4, I now have a formula that tells me what my process width is. 6 times S bar divided by C4. Or I could use the other estimate for a population standard deviation, which is R bar divided by D2. So I have 2 options here to calculate my process width. Each of them will give me a correct answer. They will be slightly different, but the difference is minimal. We're now going to run through an example and calculate the standard deviation of the populations using the 2 formulas that we've just talked about. A few minutes ago in the video, we looked at the standard error of the mean as a form to calculate sigma, or the standard deviation of the population. And of course, in the video, we said, well, we're not going to actually use that because studies have shown that a better estimate of that population standard deviation is given by our R bar formula or our S bar formula. So as you can see here in the spreadsheet, we've calculated the standard error of the mean-based standard deviation as being 15.64. Well, now we're going to calculate that standard deviation of the population using the R-bar formula, which was R-bar divided by D2. So my R-bar for this example, we're going back to the foam seat example, and I've already calculated, my control chart and done some calculations here. So I've got my R-bar here in cell H3. R-bar divided by factor lowercase d2, which is in the appendix in my textbook. So that turns out to be 3.078. So my R-bar estimate for standard deviation of the population is 15.65. For the sake of comparison, we're going to calculate the population standard deviation also using the S-bar formula. In order to use the S-bar formula, I need to calculate the average value of the subgroup standard deviation. So my S-bar is going to be equal to the average of these standard deviation metrics for each of the subgroups. So I'll select all 21 of my subgroups and calculate my S-bar value, which is simply 15. 15.1.06. So S-bar population standard deviation estimate is equal to S-bar divided by C4. I look at the appendix 2 in the back of my textbook and find that C4 is actually equal to 0.9727 for a subgroup size of 10. So 0.9727 is my value, and the estimate for standard deviation of my population using the S-bar formula is 15.48. We'll now go to the formula for capability. This formula tells us whether or not our process is capable of meeting the specifications as designed. And if you recall, earlier on we defined that as being Cp, that's the name of the metric. Cp is equal to the specification width over the process width. We know how to calculate the process width now, and we know that our specification width is also given to us by the design. So now we'll run through an example of calculating the Cp value. Going to the example that we've been working on, foam density for our car seat foam. I look at my Excel spreadsheet, and the first thing that I need to calculate is going to be the process width. Process width is equal to 6 times the standard deviation of my population. I've just calculated standard deviation of my population using a couple of different various formulas. So I'm going to choose one of those. I'll choose the R-bar formula, and it's equal to 6 times the standard deviation, 6 times the standard deviation of the population. So my process width is equal to 93.9, and the units here is kilograms per cubic meter, right? So essentially what that's saying is that all of the data points of my process, of my individual values, all of them fall within a range of 93 kilograms per cubic meter. That's an estimate of my process width. My upper specification limit is given to me by the design engineers. So they've told me that my specification, the highest density for this foam, could be is equal to 480 kilograms per cubic meter. The lower specification limit, they've said, well, the softest it could be is 450 kilograms per cubic meter, or the density needs to be that no lower than that. My specification width is fairly simple. It's equal to the upper specification minus my lower specification. So the design engineers have told me that I'm only allowed 30 kilograms per cubic meter for my tolerance. It's interesting to note that my process is functioning at 93 kilograms per cubic meter. Now, there's a coincidence here that I'll just point out. My upper specification limit is 480. As it turns out, my upper control limit is also 480. That is merely a coincidence, and it is not the same thing. So I just needed to point that out. Now that I have my process width and my specification width, I can calculate the value for Cp, which is equal to my spec width divided by my process width. The value for Cp, or capability, is 0.32. So I've just calculated Cp as being 0.3. What is Cp? What does that mean? Cp is essentially a measurement of variation. It compares the variation that I'm allowed to have in my design with the variation that I actually have in my process. Looking at this graphic here, we can think of the lower and upper specification limits as containing all of the allowed variation for a design. That's our specification width. The bell curve here represents the distribution of the actual products made on the line. Of course, we know that that distribution comes from samples that I've taken, and so I'm using some statistical calculations to estimate all possible products that are formed on the line, right? And that's what we've been walking through in this video, is how we calculate that. So this bell curve is a representation of the variation in the process. This specific example on the left shows process variation that is greater than the allowed variation in my design. That indicates a very poor process. It's not capable of meeting the design specifications. Just by looking at this, I could tell that the Cp value is going to be less than 1, meaning that the variation in my process is greater than the variation in my specifications, right? So the denominator being larger than the numerator in the Cp fraction. So we see over here on the left and on the right-hand side that there is a percentage of samples that are going to be outside of my specs and basically bad products, rejected products. So there is a probability that on this production line, with the example here on the left, that I'm making products that are not good and that will be defective. On the right-hand side, again, my lower and upper spec limits contain the allowed variation in my design. Notice, however, that the bell curve of the process indicates that there's less variation in my process. So what I'm saying here is that I've calculated the expected values of all of my products by calculating my process width, and it falls within the spec limits. This is wonderful. This is good. This is exactly what a process needs to be. It needs to be functioning within the lower and upper spec limits. My Cp value for this process is going to be greater than 1. Now, if it were equivalent to 1, I would simply have these lower and upper tails of the product distribution. I would have those really right next to right next to the upper and lower spec limits. So that's what Cp is. Cp is a measurement of variation, and it tells me how much variation I have in my process versus what I'm allowed by design. Any Cp value less than 1 means that the process is incapable, and any Cp value greater than 1 means that it is capable. However, there's also another issue that's being ignored here. When I calculate my process width, I'm calculating the amount of variation, but I am not taking into consideration whether or not that process is centered. For example, taking a look at this chart, I see that I have my lower specification limits and my upper specification limits, and at the very top example, I have my process average, and I have the distribution of my data points, and the variation is less than the specification limits, so my Cp value is going to be greater than 1. The next example down here, however, has an amount of variation that is identical. In other words, the distance from the upper tail to the lower tail is the same as the previous problem, but my process average is not centered on my design nominal value. It's not centered on the target specification. It's centered close to the upper specification limit. Clearly, we can see there's a lot of products that are being made outside of the spec limits. The problem with Cp is that I don't know this. I don't know it because it does not take into consideration where the process is located. It only takes into consideration the variation in the process. As seen in the example below, this process is considered not capable because the variation is greater than the specification limits. However, the second example, everything indicates that it's okay. My Cp value says that it's okay, but it is not always meeting specifications. The solution to the challenge with this weakness of the Cp value is to calculate a new value called the Cpk. The graph on the upper left shows a histogram or a bell curve that represents the process data, the variation in the process. And then, of course, I have the red bars on the left and the right representing my specifications. Looking at this figure, I can tell that all of the variation of my process falls within my specifications. So like we've talked about with CP, the value of this, the capability is 1, CP of 1. If we look at another example, exactly the same specification limits and exactly the same variation in the process, this also has a CP value of 1. Clearly, there's a problem, though, because the process, although capable, is not producing parts within specifications. By definition, capable simply means it has a CP value of 1 or greater. And intuitively, that might not make sense because you think, well, the definition of capable is whether it's meeting the customer specs or not. But for the technical definition of capability, when we're referring to CP and CPK, capable means a CP value greater than 1. And in this example here on the right, although capable, I'm still not meeting my customer specs. What I need to do is figure out where the center of the process lies with respect to the specification limit. So I need to figure out if the process is centered. I can do that very easily. To find whether my process is centered, I start out by taking my upper spec limit and subtracting the process average. I subtract my X bar value, or process average, from my upper spec limit, and it will tell me how close that process average is to the upper spec limit. However, that's not enough. I still don't know whether the amount of variation in my process is still basically spilling over the specification limit. Clearly, I can see by this graphic that it is, but what happens if, for example, I have a very, very tiny amount of variation in my process? The fact that my process average is close to my upper spec limit, I mean, that might concern me, but if this is the amount of variation that I have, as seen with this green histogram, if that's the amount of variation I have, I mean, I don't really care because all of my data points for my process are still within the spec limits. Now, of course, I do care because I should have that process centered. But there is a distinct difference between these two different data sets and the amount of variation that's present. So in order to account for the amount of variation, I divide my upper spec limit minus the X bar, I divide that by 3 sigma. Of course, sigma is my population standard deviation that I estimate by taking R bar divided by D2 or S bar divided by C4. This formula, the upper spec limit minus X bar divided by 3 sigma, will tell me my CPK value. In our discussion of CPK up to this point, I've been referring to the upper specification limit in the formula. Let's look at an example where our process distribution is actually closer to the lower specification limit. In this case, if I use the upper spec limit and the process average in the formula, I'm going to get a skewed result. It's going to give me a result that is much better than what I think. The reason being, well, it's closer to the lower spec than the upper, so in this situation, I should be using the lower specification limit to calculate how close the process average is. So there are actually 2 formulas for CPK. The upper spec limit minus the process average divided by 3 sigma, or the process average minus the lower spec limit divided by 3 sigma. We use both formulas and then select whichever of the 2 is the smallest as our CPK value. Let's walk through an example using the foam seat data from our production line that creates foam for car seats. We'll walk through calculating CPK for that. The upper specification limit is 480 kilograms per cubic meter. And I've calculated my X bar, or the average of all of my data points, to be 465. I divide that by 3 times sigma, and I've calculated sigma based on my my estimate for the population standard deviation of R bar divided by D2 as 15.6 kilograms per cubic meter. That gives me 25 kilograms per cubic meter of distance between the upper spec limit and X bar. So basically my process is centered 25 kilograms per cubic, 25 away from the spec limit. Essentially, that's also telling me that I have 3 standard deviations of data above that center point. So above 465 kilograms per cubic meter, I have 3 standard deviations worth of data. Now, the total amount of data above my process center point is 3 standard deviations, and that's equal to 46.8. So I divide 25 by 46.8 and get 0.53. That's my CPK value. It tells me that my process is not centered and that the amount of variation that I have in the process is too much. It's spilling over outside of the spec limit. Now let's look at an example where the amount of variation in my process is extremely low. I don't have an exact number for the CP value, but we know that it's a very, very high value. However, it's still centered at the same point relative to the last example. My upper spec limit is still the same. My process average, 465, is still the same. The difference here is that my standard deviation, instead of being 15, is now only 6 kilograms per cubic meter. Computing that, I get 25 over 18 and a CPK value of 1.38. Now my CP value is going to be a lot higher than 1.38. The value that I have in measuring the CPK is that while it does tell me that the process is making products within the spec limits, it's also telling me how close I am to those spec limits and how centered the process is. If this process were also centered and had this limited amount of variation, I would see a CPK value much higher than 1.38. Looking at this image to wrap things up, we can see that CP does have some limitations. It does not tell us how centered the process is, but it does a very good job at telling us how much variation is in the process compared to how much variation we should expect because of our specifications. CPK is an excellent indicator of how centered the process is. CP and CPK should be used together to give us a better indication of variation and centeredness.
Okay, so what he left out was how to actually figure that in Excel. So you got through, showed you how to do CP, and once you've done CP, the Excel work for CPK is pretty simple. So what you want to do, just like he showed, we've got I-15, which is the upper spec limit, minus I-4, which is X bar at 465, divided by 3 times, he's using the R bar standard deviation. And that's going to give you 0.324. And then down here, we start with X bar, and we subtract the lower spec limit, 450, then divide by the same denominator, 3 times standard deviation. Gives you 0.316. So in this one, it's closer to the lower limit than it is to the upper limit. So the way you would do that in Excel is you can do this min formula. So this is the upper limit, comma, lower limit, and it'll just pick the minimum of the two. And that's how you do CPK in Excel. Now you can look through the instructor's file here, and he's got all the charts that it did. Here's the density with the normal curve, and you can trace back where all this data comes from. This is the old way of doing it. Nowadays, all you got to do is go up to insert, pull down your histogram, highlight the data, and hit that. So what you're looking at here is an example of how to figure CP and CPK. And what this particular example tells you is CP is a lot less than 1. So this process they're using to make the foam is not going to make it within spec tolerance. So they've either got to get a new process that does a lot tighter a lot less variation, or they've got to loosen up the spec. And the other problem is with CPK, you're closer to the lower limit than you are to the upper limit, but not by a lot. But the CPK is so low because the CP is low. The process is neither centered nor capable of meeting the specification. What you really want is the CPK above at least 1.33. That's CPK of 4 sigma. If you can get a CPK of 6 sigma, it's great. That's 2.0 for a CPK of 6 sigma. And that is everything I've got for you on CP and CPK.